Isaac Newton said, "If you have done any good in the world, it is by patient thought." And in nothing does the patient thought of Isaac Newton show better than in his three laws and in his universal law of gravitation. That's the subject of this chapter. Kepler used data from Tycho Brahe to describe the motion of planets in ellipses with equal areas swept out in equal times, and the period squared of the motion proportional to the semi-major axis cubed. And we'll actually derive all three of Kepler's laws using Newton's three laws and his universal law of gravitation later in this chapter. But Newton did it first, and he came up with these laws, and they're amazing. Newton's universal law of gravitation is this, in concept 8.1. It's the gravitational force exerted on a mass m by a big mass m, such as the sun, located at the origin. So we're assuming here that the sun's mass is big enough so that the Earth doesn't yank it around very much. If the masses were more comparable, then they would actually orbit around each other. But that's a pretty good approximation for our own sun mass differences. The mass ratio is the ratio of the Earth's mass to the sun's mass is very small. The law is that the force that the sun exerts on the Earth is directed toward the sun, and it's directed opposite, toward the sun is in the minus r hat direction. If r hat is the vector that locates, it's a position vector, points from the origin out to the location of mass m, that's the vector r. R hat will be defined as r hat over r, r vector over r. It's in the same direction as r, but the force is in the direction opposite to that. So this minus sign in that r hat say that the force is attractive. The proportionality constants are g .67 times 10 to the minus 11 Newton meters squared per kilogram squared. The other proportionality constants are the mass of the sun, the mass of the Earth, and the distance between the sun and the Earth, r squared. So the force falls off as the square of the distance. It's called the universal law of gravitation because, as far as we know, it applies to all objects with mass in the universe. The Earth and the sun, the Earth and the moon, which orbits around the sun. And in fact, it was that orbit of the moon around the Earth that got Newton thinking about whether the force of an object such as an apple falling toward the Earth, whether that force would extend all the way to the moon and possibly, just possibly, be the force that holds the moon in orbit around the Earth. You can't have a circular motion, uniform circular motion, without a force, centripetal force, pulling it toward the center. Same thing for an object that's orbiting around the Earth. In order for it to go in a circle, there's got to be a force pointing toward the center, and that force is gravity. And Newton was right. The moon does obey this law. The Earth in its orbit around the sun, it's universal in the sense also that the sun in its motion around the center of our galaxy obeys this law, where m, big M, would be the mass inside the sun's orbit, little m would be the mass of the sun, etc. This law also applies to satellites, to rockets, as they move through space, And so it's a universal law, very, very important law. And this is the key for us, along with Newton's 3 laws, in order for us to predict Kepler's laws. And I can't emphasize the Newton's prediction of Kepler's laws in the late 1600s in Newton's Principia. I can't emphasize it too much about how important that was to science. Before that we had Aristotle and Plato and some philosophers, and it was really philosophy. There wasn't really anything really very quantitative about it. It was Kepler and Newton who came along and said, hey, I think we can describe nature with mathematics. And I think that the mathematics can do a pretty good job of describing nature. And as you will see later on in this chapter, they do an excellent job. The mathematics describes the motion of our planets to something like 0.1%. I can't remember exactly, but it's really, really accurate. Okay, that is 8.1. 8.2, prove that the gravitational force given by equation 1 is conservative. Luckily, we have a concept 415, which says that a spherically symmetric central force is conservative. Okay, let's remind ourselves about what, first of all, what's a central force? A central force is one that can be written namely, a central force has something out in front of r hat. So it's either, this could be positive in the case of two positive charges that repel each other. This radial component of the force would be positive because the force would be in the radial direction, outward, away, push the central positive charge pushing on the outward positive charge. For negative charges, or one positive and one negative, for example, then the force is attractive and this would be negative. The same is true for gravity. Gravity acts like, unlike charges, it's always attractive. So in that case, for gravity, Fr is just this beast right here, minus gmm over r squared. So that says that it's central because it's proportional to r hat. What about spherically symmetric? A spherically symmetric force is one for which F of r, or F sub r, is a function only of r. It doesn't depend, if you think it in spherical polar coordinates, doesn't depend on the polar angle, it doesn't depend on the azimuthal angle, it only depends on the distance. That's what we mean by spherically symmetric. Is this gravitational force spherically symmetric? And you say, well, I have to check to see if Fr, the r component of the F, depends only on r. And does it? Does it depend on theta? Does it depend on phi? No, it doesn't. It only depends on r. So we're good to go on spherically symmetric. We're good to go on central force. Therefore, by concept 4.15, the force is conservative. So gravity is a conservative force. And you already knew that for the uniform gravity near the Earth's surface. We've dealt with that a lot. The gravitational potential energy is mg times y, a coordinate measured vertically upward. Now, for the next concept, but this is new for the case of a this is not a uniform gravitational field. It's not a constant. It depends on r. And near the surface of the Earth, you can separate all of this mess out except for m and get F equals mg, where g is pointed in the minus r hat direction. All right, now we want to derive the potential energy associated with the gravitational force given by equation 1. I'm going to do a poor man's derivation of this and write down the potential energy. That's the gravitational potential energy associated with equation 1, Newton's universal law of gravitation. I'm just going to write that down and prove that it gives this force. I'm going to recall that if a force is conservative, then it can be written as a negative gradient of a potential energy. That's concept 410 that we discussed earlier. And I'm simply going to verify that substituting this u in here will recover this force. The other way to do it is to integrate, do the work done by the force, and set that equal to the negative change in potential energy. That's probably the more direct way. This way is equally valid. It's kind of going backwards, but it still shows that this is the correct potential energy. So I want to take that gradient, but u depends only on r. So that'll be du by dr, r hat, plus some other terms. If you write the gradient of u in spherical polar coordinates, look it up at your favorite place online. The first term that you'll see in that is du by dr, r hat. Then there'll be other terms involving the derivatives of u with respect to theta, and the derivatives of u with respect to phi in spherical polar coordinates. But u doesn't depend, well, F doesn't depend on theta and phi. It's a spherically symmetric force. So we only have to worry about this term, and let's see if that gives us the correct force. Here's that minus sign, and now we need to take du by dr, where u is given by this. Well, this minus sign kills this minus sign. The g, m, and the m all can come out. And all we're left with is the d by dr of 1 over r, r hat. Well, you can all take that derivative. because that's r to the minus 1. And this is an ordinary derivative now. Don't have to worry about the partials because it only depends on r, not theta and phi. So derivative of r to the minus 1 is minus 1 times r to the minus 2. So that minus sign comes out. And the minus 1 over, we get minus 1 over r squared. There's the minus 1 over r squared. And here's the r hat that comes along for the ride. And this agrees with equation 1. And so that is what we set out to prove.